Guys, something happened today. Amber needs her name. It's starting a rumor. I just need to find it. Yeah.
All right, everybody, I think I'm going to go ahead and get started. We've got 3 people in the Zoom here today, so I hope between that and everybody who is physically here, I've got most of you guys all here. Welcome to Thursday. I hope that you're having a good week and that you're smoothly gliding in towards finals coming right up. Speaking of which, we do have our final a week from Tuesday. It's going to be, I think, at 5 o'clock, and I'm going to have a review material folder in Canvas ready soon. It's been kind of a tough week for me. I'm not really on top of things, so I'm still working on that, but I'll get to it as soon as I can. Couple of announcements before we get rolling. My other class has a test early next week, so I am going to come in for some extra office hours over the weekend, and I may as well invite everybody to those. And they will be in person or in Zoom. So first of all, just quickly what my office hours are going to be is a little bit extra. I should also mention that I do have office hours tonight at 5:30, like always, right after class, pretty much until 10 o'clock I usually take a dinner break around 7, so I'll be gone for an hour and a half or something, but I'll be mostly around if you want to stop by. However, if you're stopping by in person, you should stop by here. I am just going to stay here because I've been told that the room outside my office is being closed down for a while. So it's not, I don't even know if I can get into my own office now. So it could be interesting. But feel free to stop by tonight if you have things you want to talk about. But I'm also going to have some extra hours. So on Sunday, I'm going to have some extra hours from 1 to 3 p.m. And then again, my usual hours starting at 8 p.m. in the evening. And then on Monday, I'm going to do a very similar schedule, 1 o'clock until 4 o'clock, and then after 9 p.m. So I have quite a bit of office hours. My other class has a test, and I was gone for a week and got behind, and I just kind of feel bad. So I'm trying to make up a little bit of it to you guys by just trying to be around a little bit more now. Hopefully by the weekend, I'll be actually in my physical office for those office hours again. Also, originally I had set this current homework assignment to be due, I think, on Saturday night. And it doesn't make a whole lot of sense to have the homework due Saturday night and then come in with a whole bunch of office hours on Sunday. So I decided to just make the homework due on Sunday night. So on Sunday, you have an extra day now to finish up that next assignment. And then will be one more homework assignment next week. I'll probably try to stick firm with Saturday for that one if I can. We'll just play it by ear, see how things go. But that's kind of my game plan. Is everybody clear on that? Okay. Also, Dr. Guerrero is here today, observing me. We're partners on a little project, so he's observing my teaching. I'm observing his teaching. He's not here to watch you. He's here to just watch me, hassle me about stuff. So, anyway, just wanted you to know, in case you're wondering. Or it could just be everybody's falling in love with combinatorics. The word's getting out, guys. Everybody's coming. So, yeah, so I'd like to kind of go back to where we were on Tuesday, and we're going to kind of develop a few more results here and eventually get around to doing some group work together in class in a little while. But before we get to that, just reminding you, we're talking about graph theory, of course, and specifically colorings of graphs, how we can color graphs. Remember that the rules are that any 2 vertices in the graph that are adjacent to each other have to be colored different colors, right? That's the main rule. And so let's say that I have K colors available to me, right? If I have K colors, I don't have to use all of them, but if I have K colors available to me, we're going to define P sub G of K. This is going to be the number of ways that we can color our graph G using those colors, some or all of those colors, right? So it's the number of K colorings of G. So we defined all of this, right? On Tuesday, we kind of explained this notation a little bit. All right. We did a few examples last time. Let's just kind of warm up again, remind ourselves how this is working. Let's say we have a graph that has no edges. No edges, so no vertices are adjacent to each other. Well, doesn't that just mean that every vertex you can do whatever you want independent of any other vertex? Just color it however you like. K choices, K choices, K choices, every vertex, K choices, right? If there are n vertices, right, the graph has order n, then you're going to get K to the n for this number, right? For this number here. Okay, so that's an easy one. The other one that's kind of the opposite scenario is what if we actually have the complete graph, right? K sub n is the complete graph. This means we have every possible edge between every two vertices. Then the problem now is that as soon as you color one of your vertices with any one of the K colors, then the next vertex, you can't use the same coloring. So you have one less color to use, K minus one, yeah? And then when I go to the third vertex, I have to avoid both of the first two colors. So now I only have K minus two colors left. And so this becomes one of these sort of falling factorial expressions. And in fact, if the number of colors is less than the number of vertices that you have, you eventually are going to hit zero here. Right? It's going to be a problem. You're not going to be able, you don't have enough colors to color the graph in that case. So that can happen as well. So this is the formula for this particular case. All right. We did a couple of other examples on Tuesday as well, but I want to take a swipe at a nice result about trees. Oh, question first, Khalil.
We also talked about the chromatic number. It's like doing it most efficient.
Yes, so maybe my recap is a little lackluster here. I should also put the chromatic number of G. And what was this? This was the fewest number of colors that we needed. So this is the fewest number of colors with which we can color the graph G. That's right. So again, maybe we could go back to the two examples here and write down, maybe I have just enough room here. Hopefully you guys can see this okay, but let me know. If I have no edges in the graph at all, what would be the chromatic number of a null graph, a graph with no edges? Yep. No, so there's no K now. So for the chromatic number, we don't have a K value. We just have, the question is what would be the fewest number of colors we need? Just one, right? Just one. Exactly. You just use the same color. Red, 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 red on every vertex. There's no edges. So we can just keep using that same color. What about for the complete graph? What would be the chromatic number of the complete graph again? N. Just N, right? So it's just N because each vertex has to have a different color. So the best you could do is the number of colors matching the number of vertices that you have. Question for Nevin.
On the homework that said, like, you take the complete
graph.
Then, well, what I got was that you would need N minus one.
Right.
But the thing is, like, just the graph, just the vertex. Without any other edges, that's like K1.
K1 would just be a single dot. Right. It's kind of a. Yeah, I think so. It doesn't really make sense to talk about K1 with removing edges. This is like a graph with a single dot.
Yeah.
Forget it.
Okay.
Not as interesting as we would like. Yeah. But I think the idea is that, yeah, if you remove an edge between two of the vertices in the complete graph, then all of a sudden you can use the same color for both of those vertices. And now the chromatic number would go down to N minus. Yeah, that's basically it. That's a pretty quick exercise. You just have to kind of write a quick little explanation for that. Okay, great. Wow, I have a ton of people in Zoom today. I have never seen this before. It's like, this reminds me of COVID times almost. We had like 7 people there. Okay. Anyhow. But you see that I can do it at any moment I want. I can decide to start giving out all the answers to the final exam, and I can just mute myself here. And then you guys, it'll just be our secret, right? Do it. You like that idea, don't you? These guys don't like it. Oh my gosh. I'm opening a bad can of worms right now. I'm gonna stop talking. Okay. No, I to actually do a new result now, which is I'd like to talk about this P sub G of K when we have a tree. For a tree. So remember, a tree is just a connected graph with no cycles in it, right? So there is a theorem for this. I'll go ahead and put it here for you. Theorem 12.1.7. Okay, and so let's let T be a tree of order n. Okay, so there's n vertices here. Let's just make sure. Are you guys able to see that marker all right? I'm having a lot better luck erasing today, but I'm kind of making sure my markers are working good. So then there's a nice formula for this. Let me put that here. P sub T of K, right? It turns out to be equal to K times K minus 1 to the n minus 1. Okay, so this is a theorem I want everybody to know. And I think it'll make sense to you if we, maybe I'll draw, before I do the proof, I am gonna write a proof for this, but before I do that, let me just draw a graph here so we can kind of look at an example. Just gonna draw this picture. I'll give you guys time to catch up with me and write it down for yourself if you would like. So we draw some edges here, like so. Maybe I do this, and then there's another one here. And I go down like this, and actually doesn't matter. You don't have to have exactly my picture here, but just so we have a reasonably big graph, I just want to draw something that would be a tree, right? Does everybody agree that that's a tree? No cycles, right? So it's going to have n minus 1 edges, for example. And I actually think it's pretty easy to understand why the number of K colorings is this formula. And that's because you can actually just pick any vertex to start with and just start there with a color. So maybe I start with red. Well, let's start with blue since it's a blue marker. I'll start with blue on this vertex right here. Now, I had K choices. That's actually where this K is coming from. Okay, so I have K choices. And now what I'm going to do, guys, is I'm just going to start walking away from that chosen vertex in different directions, right? So let's say I start by going off to the right here. When I get to this vertex, how many different colors am I allowed to choose for this vertex? K minus 1, right? So maybe this one, I don't know, maybe I decide to go with red now on that one. Okay, so that one's red, and now I'm just going to keep walking. I'm just going to keep walking. And by the way, since there's no cycles, I'm never going to go back to this blue vertex again if I just keep walking. Right, so let's go to this vertex right here. Right, how many choices will I have for what color to make that vertex right there? K minus 1 again, right? So maybe I choose green this time. Can you see that? That's a G. It's supposed to be a green marker. Okay, and now I've reached the end of that path. I can't go any further in that direction, but then I can go back to this junction that I was at and continue going this way again, right? So now let's say I go to this vertex. How many choices? K minus 1. Do you see that? So that maybe I do, this one's brown. Maybe I just keep going like this. I'm going to have K minus 1 choices everywhere, right? So there'll be maybe K minus 1 choices there. That's maybe black on that one. And then, of course, we can go back to blue on this one, but we have K minus 1 choices for every subsequent vertex after the first one. Okay, so let me actually try You kind of have the idea. Then, of course, we have to go the other direction and finish coloring everything to the left as well. But it just follows the same idea, right? So it's nothing too crazy, right? It's pretty reasonable. Let's write down the proof of this, how this might look in terms of a write-up. So for the proof of this theorem, are we good?
I was saying, you could technically just go alternate between blue and red, right?
Yeah, you could. Yeah, you could. Even if you only had two colors, you know, you could. If you had two colors, if K was 2, what would the formula be, by the way? If K was 2?
2.
It'd be 2. Does that make sense that it would be only 2? Let's say your colors were blue and red. If I start with blue here, then I'm forced to make this red. I'm forced to make this blue. I'm forced to make this blue. This has to be, you don't have any other choices the rest of the graph, right? So it all just comes down to which color did you choose here, and then you have to alternate the colors throughout the rest of the graph, you see. Yeah, exactly. That's exactly right. Yeah, it'd be exactly 2. Yeah. Right, let's put this proof down. So what we can say here is that choose any vertex and there are K choices for its color. We have K choices there. This is the task of coloring the tree. And the first vertex, whichever one we choose, it will have K choices for how we color it. And then from there, subsequent vertices, so I'll write this word out here, subsequent vertices, meaning other vertices that we consider later, subsequent vertices on any open path. Notice I didn't say closed path. There are no closed paths. There's no cycles in this graph. So it's going to be an open path. Must be subsequent vertices on an open path must be colored with a different color than the prior vertex. So you're kind of doing this in order, right? There's a prior vertex there, and you just have to choose a different color than whatever color you used on the previous vertex. Let's try to write this a little bit easier to see here. So let's just say hence K minus 1 choices for each. And this is for any open path. So we can actually therefore go out to every vertex of the whole graph that way. Okay, so then finally by the multiplication principle of counting that we learned way back at the start of the semester, right? By the multiplication principle, the number of K colorings, so this is piece of T of K, is just going to be K times K minus 1 to the N minus 1. Everybody okay with that? Pretty reasonable. I have a little nervousness about it. I want to ask you something if I could. What if I chose to do something different? I'm not going to draw the whole thing again, but what if I chose to do something different? Let's say I choose any vertex, there's K choices, so maybe I choose black right here. Right? So there were K choices there. Well, what if I decided to jump over to the end here and say, well, now, wait a minute, if I didn't go along an open path in some kind of a subsequent sequence of vertices, what if I just said, I'm going to color this vertex next? Wouldn't it be true that I would still have had K choices there? Feels that way, doesn't it? Which now that's going to bother me because I don't see 2 factors of K in the formula here. The reason that it would not be wrong to do that, but the issue will then be that when you look at this vertex, how many choices do you have here? Oh, it's going to depend, isn't it? What if I make both of these black? Then I would have had k minus 1 choices. But if I make one of them black and one of them red, then I would have had k minus 2 choices. Now you got cases. Now you got cases. Now it's like, okay, depending on what I did here, that affects what I do here. So it's not that it's wrong to sort of jump around and color things in a different sequence in the graph than what I've outlined in the proof, but it's not going to be an easy way to do the counting problem. Right. And we've all seen examples of this all semester long where, you know, there's more than one way to sort of skin a cat. There's more than one ways to break up a counting problem. Sorry, I don't know where that came from. Okay. What's that?
Oh, I'm thinking Dr. Murphy.
Does he say that too? Okay. I don't really hang out with him, so I don't know where. Anyway, you know what I'm trying to say. Yeah, so there's sometimes multiple ways to do the task of coloring a graph or of counting an arrangement of something. And it might be much easier or much harder depending on how you've chosen to set it up. So the way I've done the proof here is lined up in the best possible way with this formula where you don't have to use any cases, you see. That's kind of the idea behind it. Okay, so I think that's a nice result. And if that was a nice result, the next one is really going to be a nice result. So I'm going to show this one to you. Oh, I'm so excited. Do you realize this is the second to last class? What am I going to do with myself for weeks on end after next week?
Yeah,
I'll probably have to find some mountain to climb. Yeah, I don't know. I don't know. When I was a student, you know, I loved teaching. I've always loved teaching. And I would go into a classroom on the weekend and just teach the material to myself. So maybe I'll just do that. If any of you wants to come, you can. Just to add to the formality of it. But I'll just probably be here. I'll just be here lecturing to myself. See if I learn anything. I don't. Did I pick that up? I don't want to break a leg. That's what I'm doing.
Teach for 17. No.
417.
Foundation.
I got it. No, you can teach me.
We're down. We're down.
This is a nice result. It turns out that for every graph G, it turns out that PG of K, this expression that we've been looking at today, right, is always a polynomial in K. It is always going to have the form of a polynomial. So we have some idea what type of a function it is as a function of K. It's going to be a polynomial. And in fact, so before I write the proof, this gives me a way of talking about what this symbol means. So P sub G of K is called the chromatic polynomial of G. Polynomial, sorry, spell. The chromatic polynomial of G. So we have the chromatic number of a graph, and now we also have the idea of a chromatic polynomial of a graph. Okay, so let's talk about the proof of this result. Actually, we kind of try to give a proof. And the way we're going to do this is we are going to use a reduction process. So we're going to take our graph G and we're going to somehow break it down. We're going to reduce it into a simpler graph, and we're going to repeat that simplification process again and again and again until we get down to something such as maybe a graph with no edges. This is obviously a polynomial. K to the n is just like, that's like x to the fifth or something, right? That's definitely a polynomial. So this is going to be the idea. So here is what we're going to do. We are going to let X and Y be adjacent vertices in the graph G. That's the start of our proof. By the way, what if I always like to ask myself, well, what if there are no adjacent vertices? If we're trying to do something, we've got to be able to do it. If there are no adjacent vertices, that would mean there's no edges. If there's no edges, then I'm already here. It's already a polynomial. So I'm good. Yeah.
So, if they're adjacent vertices, it exists an edge between them?
Right. So that's what it means. And now here's what I would like you guys to do. Not in the middle of your proof write-up, but somewhere in your notes where you have a spot, I would like to actually show through the use of an example how this reduction process works. So I think I have room right here. I'm just going to take my graph G. So give yourself enough room to kind of do this picture with me. I'm going to just do an example. So I'm going to start with a vertex at the top and then 3 edges coming down. And then I'm going to make another edge down here and another edge down here like so. And then we're going to connect across, and then down like this. This is going to be my graph G that I'm going to start with. Okay, just for the purposes of it, you'll understand the reduction process so much better if I have an example running alongside the whole thing, okay? So, and what I'm gonna do is, let's just say this is X and this is Y. Okay, so we'll pick 2 vertices, X and Y. What we are going to do with this graph is we are going to replace it with 2 graphs that are both simpler than this one, that are both somehow reduced from this one. The first graph is the graph that I'm going to call G1. So give yourself another space for a picture here. What G1 is going to be is the same exact graph as G, but without the edge XY, right? So I'm going to redraw the same picture again, but without the edge from X to Y. So there we go. There's X and there's Y. We've taken that one edge out. Nothing else has changed. We've reduced just by one edge right here. Is everybody with me? Okay. But then I'm also going to do a different graph over here. This is going to be G2 on this side. And in a minute, I'll come back and add the text that goes with this. But I just want to have the picture up here first. The way we're going to do the graph G2 is we are going to merge X and Y together. We're going to like compress that edge down and make X and Y into a single point. Let's see if I can draw it. So we start at the top. We've got the 3 vertices coming down just like before. And then we have this edge on the left. But that edge connects to Y. But guys, this is X, but it's also going to be Y. I'm going to merge those 2 vertices together. So this edge then gets hinged up like that. And then this vertex on the right, it connects to Y, but Y is now here, right? And then we still have this one arm coming down like that. By the way, you'll notice that in the original graph, I have what? How many edges do I have? 1, 2, 3, 4, 5, 6, 7, 8 edges here. And then how many edges do I have over here? 7. And how many edges do I have over here? 1, 2, 3, 4, 5, 2, 3, 4, 5, 7, right? Yeah. This is what we mean when we say it's a reduction process. The number of edges is going to be going down. The number of edges is going to be going down. Okay, so let's write some words now back to our proof again. So let's explain what we've just done. Let's let G1 be the graph obtained from G by removing the edge XY. Hold this over just a little closer if you don't mind, so everybody can see this clearly enough. Okay, so that's G1, and then we're going to let G2 be the graph obtained from G, right, by merging X and Y to a single point. Okay, that's the idea here. That's the idea. Okay, back over here, we're gonna need a little more room. This is a pretty big result, so we shouldn't expect this to be like a two-line proof. It's gonna take a little bit. It's gonna take a little bit to get this. Any questions though so far? Is everybody following me okay? Yeah, so this is just setting it all up. Of course, what we ultimately would do is we would then take G1 and do the same thing. We would remove an edge, we would merge, we'd pick some edge here, we'd remove it, then we'd merge it. We do the same thing with G2, we'd remove an edge and merge it, then we'd be down to 6 edges, right? All the way along the line, and then 5, and then 4, and then 3, and then 2, and then 1. And eventually you'd have a whole bunch of graphs, all of which had 0 edges. And that would be just those null graphs, k to the powers, the powers of k. Right, so that's going to be the idea. Okay, so now here's what we're going to say, guys. Continuing with the proof here. The number of k colorings of G1. Okay, I'm going to look at G1 right now. That's the graph on the left, right? I can think of those colorings in 2 parts. Namely, this is the number of k colorings of G1 with X and Y the same color in the graph G1, guys. Are X and Y allowed to be the same color? They are, because we removed that edge. We couldn't do that in G, but in G1, X and Y can be the same color because we removed the edge. Those 2 vertices are not adjacent. Okay, and then I'm going to say plus, excuse me, the number of k colorings of G1 with X and Y different colors. Okay, that's going to be the idea here. Would everybody agree that all of the colorings of G1 are occurring or being counted in one of these places, right? The colorings of G1 where X and Y are the same color, and then the colorings of G1 where X and Y are different colors. If I add those together, aren't I going to get all colorings of G1? In other words, what we have on the left, of course, is just P G1 of K. That is what that is on the left side. That is what that is on the left side. The number of K colorings of G1 by notation is just this expression. Yeah. Okay. Now, what do we have going on with the terms on the right side? K colorings of G1 with X and Y the same color. I would like you to think with me for a minute. If I tell you ahead of time that X and Y are both the same color, I don't know about any of the other vertices, but X and Y are both the same color. Would you agree that that is in a correspondence with a coloring of G2?
Yeah.
Let's say that the X and Y are both green, right? If X and Y are both green, then if I merge X and Y together and I have green on that, and I leave all the other colors of all the other vertices the same, right? Wouldn't there be the same number of each? If I go home and I figure out how many ways can I color this graph so that X and Y are the same color, and Maria goes home and figures out how many ways can she color this graph, we would come back with the same answer, right? If I have 10 ways, she'll have 10 ways, right? Because whatever same color I use here would be equivalent to just coloring that merged point with that same color and doing everything else the same. In other words, this is just PG2 of K. Fair enough. And then what about if X and Y are colored with different colors? I don't have to color them with different colors, but would you agree that if I color G1 such that X and Y have different colors, that then I could just as well add the edge in and nothing changes. And I then have a coloring of G. So if I choose to make this blue and green, then over here I can still use blue and green and I have a perfectly good coloring. Again, if I go home and I color G1 as many ways as I can with different colors on X and Y, and Amber goes home with G and she colors this graph as many ways as she can, right? She and I are going to come back the next day with the exact same number of ways of doing it.
Or you'll be right.
Or you'll be right and I'll be wrong.
No, it wouldn't work that way.
Probably I'll be wrong. Trust me, I know how to mess things up. Okay, so this is just this. This is just PG of K. Right? Just as a perfect correspondence there. So that's kind of the idea. So, guys, that means we are really in good shape here because thus, right, if you guys are with me on this, I now know that P sub G of K is equal to, let's just subtract it over, P sub G1 of K minus P sub G2 of K, right? In other words, the chromatic polynomial of G can be written now in terms of the chromatic polynomials of G1 and G2, each of which has less edges than G did, right? And so what I could do next is I could say, okay, now I'm going to take G1 and G2 and do the same reduction process on them. And what eventually happens, guys, if you keep doing this sort of two subgraph decompositions, you eventually get down to no edges. You get a bunch of pictures of dots at the bottom of the board, which is probably about 10 floors below us here, right? And by the time you get there, all you have is a bunch of null graphs, right? The number of vertices, by the way, we should be clear here, the number of vertices of G1 stays the same as the number of vertices of G. Mm-hmm. But G2 actually has one less vertex because the merging of X and Y has taken two vertices and kind of collapsed them down to one. So edges and vertices are only going down as we do this reduction process. So I'm just going to say continuing this process with G1 and G2, we obtain graphs. I'm going to call them G11 and G12. That's kind of the two subgraphs of G1. And then I'm going to use G21 and G22, right? We obtain graphs G11, G12, G21, and G22 at the second step. And so on. I'm going to just kind of go dot, dot, dot here. This is kind of an algorithm. It's a process. We're not going to spell it out forever, but we get the idea of how this works. At the end of the day, all we have is a whole bunch of null graphs. So each of these terms will get replaced by two more terms. And then, so that'll be a total of 4 terms. And then when we do it again, we'll be up to 8 terms. And then 16, and so on and so forth. But eventually, what we end up with, and let's see, how did I write this down? We eventually obtain a collection of null graphs. Just to be very clear, I don't know if I've been using that word very heavily, so just let me make it clear that just means no edges. Graphs with no edges whatsoever. Whose chromatic polynomials, I should say, have the form oh, what is it? It's going to be K to the, well, that's the number of vertices. And we don't know what that's going to be because the number of vertices keeps changing. So I'm just going to say have the form K to the P for various P values. For various P values. That's basically going to be the idea. And so if you have a bunch of terms that are all K to the P, so that could be K, K squared, K cubed, K to the fourth, and they're all with pluses and minuses in front of it, depending on, I mean, you have to be careful, right? This one's going to be like something minus something minus something minus something, blah, blah, blah. So you're going to have double negatives and stuff like that. But it's just positives and negatives of powers of K. That's a polynomial. That's a polynomial. So this just gives me a polynomial. Okay, so I guess I will just go ahead and write one more sentence here, and then I think we're going to be good to go. Okay, so P sub G of K is, let's just say, consists of sums and differences of powers of K. Hence is a polynomial. Oh, I like that. I really like that. I really like that one. Does it make sense? I know it's kind of wordy. It's very typical of these sorts of things. We tend to have to write.
Dr.
Right there.
Annan, can you move the computer a little bit?
I'm sorry. Scared me to death.
Professor?
Yes.
I'm kind of confused how you're like with the example graph G and when you get down to G2, like how are
Yeah.
you are you able to keep reducing it in this way?
Yeah, I mean, you will once you have G1 and G2, right, guys, you will then do another layer down where you do two more graphs down from each one of these.
Yeah.
So you split it down to another graph that has one more edge removed and one more edge merged, or two more points merged together. And you just do that repeatedly. So I think it might make more sense. I want to do an example actually. So maybe that will help clarify this. Yeah.
That would be one option.
Uh-huh. Right.
Okay.
Yep, that's exactly right. That's exactly right.
Is there anything special when positive
You will, of course, eventually get down to a point where there's no cycles, but I don't think I would, I mean, at that point, you maybe, if you do eventually get to a tree, you could then, instead of continuing the reduction process on that spanning tree, you could go back to our theorem. And just say, hey, here's P sub tree of K, and just plug in that formula, and you wouldn't need to actually go all the way down to the null graphs. I think for the purposes of the proof, it's better to go all the way to the null graphs, but you're right, from a practical point of view, if I just get myself to a tree, I'm good. Definitely good. Yeah, Maria.
Is G of K a number? Like it's eventually?
Yeah, for any value of K, it will be, I mean, it's a polynomial in K. So if you tell me that you have 4 colors available, then K is 4, and I would put in 4 for K into the polynomial and get a number.
I thought that K to the P would be like an exponential, or I'm confused.
No, I mean, instead of K, if I used X for the number of colors, it would probably make more sense. Like X to the P would be, a power of X. It's not, so that's a polynomial, like
Okay.
X to the 5th as opposed to
Okay,
5 to the
Gotcha.
X. Yeah, it's because we're using a K here. I think it's a little bit bizarre notation.
and P is the vertices that are left over after all the reduction?
Yeah, that P is going to be the number of vertices that's left over. So you see that changes. Like this graph still has 7 vertices. This one only has 6 now. So as you do the reduction, the number of vertices does change as you go along. Yeah, that's a good point. Let me show you another example that I think will help with this. it's actually kind of right along the lines. In fact, you guys are gonna like this because this is actually one of the homework problems.
Yay.
I'm just gonna do it for you. I'm such a nice guy. That's right. Merry Christmas. So here's the example. I forget which problem it is, but it is on your assignment for Sunday. And it just says prove that if I take the chromatic polynomial of the cycle graph Cn. I think I mentioned this one on Tuesday and said, well, later on we'll figure out what this is. It turns out that this is equal to k minus 1 to the n plus -1 to the n times the quantity k minus 1. And I would actually recommend that you guys put this on a flashcard and learn it because it's actually pretty useful. And this would be only for n greater than or equal to 3 because you can't really talk about a cycle graph if you only have 2 vertices, right? Making sense, Jose?
Yes.
Yeah, good. Austin, are you good? Awesome. Okay. So the way you're going to prove this one, guys, is any ideas? One more time. Reduction, which is, of course, how that process is explained. But because this is done by a reduction process, that is actually promoting the idea of sort of using what I would call induction. Induction, yeah? In other words, what I'm going to do is I'm going to prove that this formula is correct for n equals 3. And then I'm going to assume that it's correct for a cycle of n minus 1 size, and then prove that it's true for size n. Okay, so let's do this. But you're basically right. You're basically right. So let's do the proof for n equals 3. This is what I call the base case of induction. So the chromatic polynomial of C3. Okay, so just to be clear, C3, guys, is just this, right? I just have a triangle, basically. And can somebody just tell me, don't look at the formula on the top of the board, just tell me how many ways can you color these 3 vertices? This is really just K3 for all that matter, right? K3 is the same as C3. What's going to be the chromatic polynomial for C3? K times K minus 1 times K minus 2. Now, has anybody checked whether that would happen to be the same as K minus 1 cubed minus K minus 1? Probably you haven't, but you can. It's going to work. It's going to work. If you factor K minus 1 out of here, let's just check it. I like to do algebra. I am an algebraist. So if I factor the K minus 1, I'm left with K minus 1 squared minus 1. Like so. And what is that? That's just K minus 1 here. And then in the brackets, I've just got K squared minus 2K. And you better believe it. This is K minus 1 times K minus 2. It's exactly what we would expect it to be. And it's matching with the formula when n equals 3. So this is a check. This is a check. This is plugging in n equals 3 into the formula would give me this. Let me just make sure everybody's with me. See, if n is 3, this is an odd number. So this is a minus sign. Right? If I put in n equals 3 everywhere here, this is what it reads as. But if I do the algebra, it comes out to what we would expect it to be, which you guys already told me is K times K minus 1 times K minus 2. Right. Okay. Great. Now, excited. Is everybody good with the base case? Before I get to the really fun part, let's go to the induction step, as they call it, right? So the inductions, I need more room. Oh, this is so cool how this works. You guys better take the good notes on this because I'm probably going to grade this one because I just love this problem. I really like this problem. So now let's do the induction step. So let's assume that if I did the chromatic polynomial of a cycle graph of k minus 1, so I have an n minus 1 gone. Let's just see, the formula in this case is going to be well, by assumption, I'm going to assume that everywhere I have an n up there, now I'm going to put n minus 1. So it'd be k minus 1 to the n minus 1 plus minus 1 to the n minus 1 times k minus 1. I'm going to assume that's how the induction works. We assume the n minus 1 version of the statement that we are proving, and we're going to try to prove it for n. You ready for this? So then PCN of k is what we want to calculate. Let me, again, find a little bit of a margin in your notes because I would like to draw a picture. I would like to draw a picture of my CN. So CN is over here. I'm just drawing it out of the way so we don't get it mixed in with the proof. This is going to be CN, right? And this is what I would like to find the chromatic polynomial for. Any ideas how I'm going to get it? Press it first. Yeah.
CN represents a complete graph.
No, Kn is the complete graph. This is the cycle graph. This is literally just like an n-gon. So this is literally what I have up here. I guess for this picture, I have C7. Okay, but I just want you to imagine it as Cn. Yes.
So when you say you want the chromatic polynomial, it's not asking about like the coloring, or
I
it's
want to know how many ways, if I have k colors, how many ways can I color this?
okay.
But what's the procedure for finding the chromatic polynomial of a graph? Do we have one? Anyone?
Depend on odd or even.
It's over here. This thing right here. We can actually, because we just learned a few minutes ago that if we break this down into two graphs, right, then the chromatic polynomial, what was it? The chromatic polynomial of G was equal to the chromatic polynomial of G1 minus the chromatic polynomial of G2. So let's just put a little X and Y on our graph somewhere. Okay, and let's do the G1 graph here. So the G1 graph would look like this. Right? I'm now missing the edge. I've removed that edge. Okay. And the G2 graph, okay, I put that one here. Now, how does that one work again? For the G2 graph, I'm going to kind of squeeze the X and Y together, right? And what's that going to actually end up giving me? It's going to just make a cycle with one less edge, right? Ooh, that sounds like induction. It's going to be nice for that, right? So I'm going to have one less edge. So instead of 7 edges, I'm going to have 6 edges. Hopefully. 1, 2, 3, 4, 5. Nope, that's too many. Sorry. Let's try this again. Something like that. There we go. Does that make some sense? So G2, by the way, is just a cycle of one less vertex. Okay. Oh my goodness. That is basically going to be the key idea here. Because now, if I want to calculate this thing, isn't it just going to be, by the way, what is this a graph of? It's a tree. It's a tree. This is a tree minus the chromatic polynomial of a smaller cycle, which we have the induction assumption for. Let's check it out. So this is just equal to T. G1 is just a tree. Oh, I love this. G1 is just a tree. G2 is just a cycle with one less cycle. Check it out. This is T of K minus P Cn minus 1 of K. Right? Yeah, does anybody get the formula for the tree yet? Okay. Right, it's K times K minus 1 to the N minus 1. We learned that in the first theorem. And now we have induction, right? for the cycle of length n minus one. So let's go ahead and put that in. K minus one to the n minus one plus -1 to the n minus one times k minus one. Boy, I hope this works out. Let's see if the math is going to be nice to us here. So this is the expression. Oh, look at that. I have k factors of k minus 1 to the n minus 1, and then I'm subtracting a k minus 1 to the n minus. This first part, isn't that just k minus 1 to the n? Because I have this and another factor k minus 1 comes down. And then I have here, what is this? This is minus -1 to the n minus 1. So that is just an additional factor of -1. So I have a -1 to the n minus 1 with one more minus sign now. So that jacks it up to n times k minus 1. Is that anything like what I want? That is exactly what I want. That is the proof. Oh my goodness. I am so stoked. I am so stoked.
I don't believe it.
You don't believe it? You don't believe my proof? Oh my goodness. So, it's an interesting thing though to try to keep track of here is that if we can take our graph and reduce it in a way that we either make a tree or a cycle or a complete graph, right? We know the chromatic polynomials for those already, right? So this is a nice problem because we were able to take a cycle and reduce it to a tree in one sense and a smaller cycle in the other sense using the G1 and the G2 idea here. It's pretty nice. So I have a group work here, guys, and I just want to show you, I'm going to have you work on problem 3 first, which is to find the chromatic polynomial of this graph here. Okay, and what I'm going to recommend that you do is that you choose your X and Y, make a good choice of X and Y, right? Because what I want to do is I want to choose X and Y so that what I'm left with when I do the removing edges and merging vertices together is something I'm already familiar with. So for example, I'm getting through, so I'm going to tell you the whole thing. If you choose X and Y like this, then when you remove this edge, it goes this way. And you have the formula now for the sum. And then, of course, the other one will be you have to merge that in. So you don't, what I'm trying to say is you don't always have to reduce these graphs all the way down to just null graphs with no edges. If you just reduce them down to something familiar, either a cycle or a tree or a complete graph or something else where you've already calculated the chromatic polynomial, then you can save a little work, right? You don't have to go all the way to the end of the process. Okay, Khalil, yeah.
All right. That algebra is just not.
The algebra? What in the world did I do wrong?
No.
No.
Like, I just,
Let's see. So this is are you good? This is the tree?
Yes.
And this is the induction somewhere here, this one. I'm putting that there. So, busting out these parentheses here, let me just, if I screw this up, I'll be out of a job. Let me make sure I can do this right. I've got to try. Yeah, don't tell Dr. Glass. So if the problem is we have a witness here. So let's see. If I split out the parentheses here, this minus, right? I'll put that there. And then I'm going to distribute this minus to here, which just means I'm piling another minus sign onto that term. So I'm going to leave it as plus. I mean, I can change it to minus, but I can put it as a plus if I will put one more -1 power there. Right? And then these two terms together, right? Do you see that they both have k minus 1 to the n minus 1? If I factor that, what's left behind is a k and a minus a 1. That's just another k minus 1 to go along with the ones that are already there. And it gives me n of them in total now. Okay?
Yeah.
I hope I got that right. Okay, very good. So guys, I would like you to try to figure out the chromatic polynomial for this graph. It is problem 3 on this handout. We've got about 15 minutes. I'm going to send you, you can use any whiteboard around the room that you like and grab 2 or 3 people. And I will, how do you do it? Send these around. Okay. Gotcha. Dr. Nelson. No, she don't want to do it. You can erase anything. You can use the sideboards, the backboards, whatever you want. I'll clear this off for you. That's what they pay me the big bucks for. Oh. And actually today it's also. I'm just closing on this. Yeah, they see in this room too. Oh, we roll your head and start chilling. Excuse me, chilling, bro.
I'm straight chilling, bro.
Okay. Come on down, guys. This is group work number 12. Those of you who are out there in Zoom land, you can jump in with group work 12 if you want to. I will. You guys aren't going to make any mistakes, right? This is going to be on the internet. So. Or I could go this way. I'll go back and forth. I'll go back and forth.
So he said this number. Hey, yeah. All work well.
It's a cycle.
Yeah.
I'm just in the cycle formula. So you can use that. Yeah, definitely. Okay.
It's the same as let me keep.
Amber, do you have a group?
I don't say.
I'm expecting.
Don't you think it's break it down again? So what do you want to take out? Because that's a free second. That's a free second. We have to do more than one. Yeah. Some shit. Well, that's a tree. That was a tree once you remove it.
No, this one we're good. This one we only have one side, right? So 6 seconds.
Yeah. So then I have to find this. Or we could.
You can certainly
pick
do
which
that.
one.
If you wanted to.
It'll be fast.
You just keep doing.
Oh, we
Well,
want.
it's not really true.
It's reducing by removing and using. But that's gonna give you that. Good. Okay.
But that doesn't. It's a big tree. It's all edges of it. No.
Oh, let it go.
What would you remove? That's only it's 2 3 seconds. I can't believe it.
Let's see. We're doing here.
We are.
One looks fine. You guys happy?
I was thinking one edge.
Right. If you remove one edge, then you can use the same color. For instance, that we're just either. Exactly.
Right.
Yeah, brought all my weapons.
So then.
Yes.
We can like, I mean, Teresa was talking about.
Just reasonably. Yeah. Oh, yeah. You could try. I would have to hear what the reason is. This one I'm very sure.
We reason them.
Well, I would say, okay, this is the how to kind of get rid of slow.
Oh, I see what you're saying.
Yeah, you have like 3 minutes. By the multiplications. Now, technically, the instructions say, use the algorithm to go all the way. Okay, so I think it's not bad, where does that? And then. So we probably listen together.
Tree. They do it all.
That does not look right. Check that again.
No,
No, I think you had the formula right, and I think the algebra was simple. Anybody else need a hand right now?
Yeah, because.
That's good.
Is that right?
Looks good.
Well, like.
Yeah.
So let's do it that way.
We don't have a tree yet, so we gotta read this whole list. The rest of it's fine. Just because like it's saying, even which
Amber, can you hear me? Move me closer.
That's one of the. I think we saw if we get a tree and a size. Which is this.
I don't think so.
Yes.
I really using like the free stuff and get a tree.
You can, if you get to a tree or a cycle, you could stop and use the formula that we already just learned today. Or it's technically what this is saying here is that it wants you to kind of go all the way down to where you have just nothing but with dots. So that's gonna take a long time because, you know, you have to go several years. So if you want to just get to a place where you have.
Sorry,
down tree cycle and then use the one. How's this working out? You have nothing but trees, and so it's like, okay, I could just stop now. I think that's because you did 1, 2, 3 layers. You've got cycle here. This one breaks to that, this one breaks to that. Okay, I see. Yes, that makes, that's right. This is focus. And then on this one. Yeah, it's really good, and then we have formulas for all the lines. Right, they chose to remove this edge. So they removed that edge, so this edge is gone.
When you do it.
And then when they merge the edges together, the X, Y, and W get sort of collapsed right onto this spot. Imagine like you post this up to here.
Those ones that are.
Right.
Is not exactly the same.
Yeah, it doesn't really.
We thought, I thought about that too, but I was.
No, I don't think there's anything.
Amber,
All right.
Wait, Dr.
Yeah.
Amber,
What? What's
Amber.
Thank you, Lindsay.
It's Litzy. Can you take a picture of that example for me? I love you.
Hey, Khalil, step that way. Step that way.
Because like Hamilton, like a graph, although it has a Hamilton cycle, it's some of their edges in there. And those, yeah, those they make. You have to be able to. Isn't this just the formula, right? I don't know.
I don't know about that one.
You get it, Lindsay?
I sure did.
All right.
And.
So what's the formula then? That's what I was doing.
Yeah, I'm saying.
Like you're
Going. Yeah, that was done. It's just make up for you. Sorry. There you go, which is a. Yeah.
Oh. Start day choices for that vertex and then start coloring this. Side with here, we know the formula there. Let's put it all together. Yeah, that's coloring that way. And then just imagine you're doing two separate categories independently. Right, right.
So like right here, like stuff. What we're saying, stuff is like. Well, like A times A minus 1 and we find it substitute. I like how you're getting your own next to
I know.
Yeah, but there's a winning speaking is better than the okay, that's if you want to know what SMG1 is in terms of I got all the way to the bottom.
Let's do this. No problem.
Just putting it in place. For a tree, look at did you watch that?
Not bad.
Which is so I saw like some tree and it's just
That's great. Hey guys, just so you know, I know you're all having a great time with the graphs and so on. It is just about 5:15, so if you ever get to a place where you feel like you want to just kind of put a period, feel free to do that. Remember, I'm going to just hang out up here because of the office situation. But if you need to go, that's totally okay. We're pretty much done for the week. And next week, we're going to do Burnside's theorem. A little bit of group theory combined with combinatorics and coloring. I think it's going to be fun. Okay. And I do have the solutions to this posted, so if you didn't get a chance to finish it totally, be sure to follow up and take a look at it later. Okay? Thanks for being here today, guys.
oh I was like what?
Thank you.